Okay guys, I'll be switching gears today. We started the first class talking about intensities, both objective intensities and subjective intensities. Subjective intensities, of course, being the differences in temperature, differences in speed, differences in density, differences in pressure that drive actual processes, geological, meteorological processes around the planet. And then we switch to subjective intensities, when we compare Hume versus Kant, and we two different theories of subjective experience, one in terms of categories and classification, and the other one in terms of intensities. Intensities tamed and given structure by habit and routine, or more exactly, by the habitual association of cause and effect, of spatial continuities, and of similarities between things. So, given that we began the week talking about intensities, I think it was a good thing what happened yesterday. We got controversial. The intensity level, reached the maximum peak last night. So, we're still in the subject of intensities. So I want to end the class, this third class, coming down from the peaks of intensity that we reached yesterday, which are perfectly natural since we're dealing with, the moment you deal with social matters, particularly ones that are going to impinge on questions of social activism, that intensity levels can reach a peak. Today we're going to kind of tone it down because I want to end with, things that are more personal, things that are more, it's in the second part of today's class, and at the beginning of today's class to deal with questions about science. I began the first class saying that Deleuze borrows three reasoning styles from science. We saw population thinking, we saw intensive thinking, and topological thinking that I'm going to flesh out a little bit more today. But as I said in that class, Deleuze does not want to follow scientists wherever they want to go. Deleuze wants to conceptualize scientific fields. I'm going to stop using the word science because, as I just wrote on that blackboard, science just like that is a reified generality. It's just like the market or the state. There is no such a thing as science in general. And we cannot say, well, science is, and then followed by some kind of lame description of the scientific method. Experiment, proposing hypotheses and then testing them in the laboratory. That doesn't tell you anything whatsoever about any particular scientific field. Like everything that we've been doing in this class, we need to replace a unified, reified generality. There's a single thing in which sameness is what counts. That which is shared by chemistry, that which is shared by physics, that which is shared by biology, the scientific method, by a plurality or a population of individual scientific fields, singular scientific fields, each field having its own history, each field having its own point of origin, and, at least potentially, its own death. That way, scientific fields become just part of the ontology that we've been talking about here. We're not introducing anything new or different. Plus, in addition, this gives you a much better way of assessing questions of absolute truth. When you speak of science in general, and many people do, many philosophers of science do, this is in fact the norm to talk about science as if it was one monolithic thing, is there, and your typical philosopher will use as his or her paradigm of that one unified thing classical mechanics or relativistic mechanics or quantum mechanics. That is one very, very successful field from physics. Classical mechanics, Newtonian mechanics is typically the one that is used the most because that one was extremely successful in the 3 decades under which it was developed. It reached, and as we will discuss later on, a point of synthesis and unification in the 19th century that other scientific fields envy, because it was everything reduced to a single equation from which gravity, electrostatics, geometrical optics, and mechanics could be all derived. It's called the Hamiltonian, kind of master equation. And it was also given what is called an axiomatic form, just like Euclidean geometry. An axiomatic is a very specific logical form in which a few indubitable truths or a few self-evident truths act as axioms. Those you don't have to prove because they are self-evident. And then using the most mechanical of all mechanical recipes, the recipes of deductive logic. Deductive logic simply moves truth from general truths to particular truths. Like in the Aristotelian syllogism that I mentioned in the first class. All humans are mortal. I am human. Those are the two given ones. And from there, the mechanical recipe can produce I am mortal. Now, that doesn't sound very exciting because it isn't very exciting. Deductive logic is the most mechanical form of logic. It was mechanized 2,500 years ago with the syllogism. It was extended into Boolean logic in the 19th century and into other types of logic later on. And so it's perfectly well known. But it doesn't produce knowledge. It simply moves truth from some sentences to other sentences, or from some propositions to other propositions. Inductive logic, which is very, very different, it begins with particular truths. Imagine that we have a bunch of jewels here, and I'm going, this emerald is green, this emerald is green, this other emerald is green, three particular truths, and then I go, all emeralds are green. I go from the particular to the general. That is to produce some kind of knowledge, because it's generalizing. There is no mechanical recipe for inductive logic. No one has ever been able to do an algorithm that automatically produces general truths from particular truths. It continues to be the holy grail of artificial intelligence, at least one of the two branches of artificial intelligence, the symbolic branch. And they have achieved a certain relative successes with a few limited forms of inductive logic, but nevertheless inductive logic remains an elusive goal. So when you have an axiomatic, like in the case of Euclidean geometry, and with that pedigree going back, $2,500 to the Greek civilization, then that becomes a kind of goal for scientists to aim at. If we could only give an axiomatic form to all of science, that would be the dream of scientists. A few indubitable or self-evident truths, and then everything follows from the simplest of mechanical algorithms, deductive logic. So everything is kind of self-contained, and we have reached a final truth in the form of an axiomatic. Now that is a dream. That is a dream that scientists have, that some scientists have anyway, because it's typically a dream of physicists. Chemists, for instance, know that there is no such thing as a final dream. Chemists are in the business of synthesizing new molecules from previously existing ones. And they are perfectly aware that once you synthesize a new molecule, then that molecule can be combined with this other molecule to synthesize an even newer molecule. And the newer one can be combined with this other one to synthesize an even newer one. And there is no limit to the space of possibilities of molecules that you can synthesize. So there are very few chemists in history that ever said, well, one day chemistry will be reduced to an axiomatic form. Nevertheless, the dream exists, and as I said, when in the 19th century classical mechanics, Newtonian mechanics was given an axiomatic form, and all the main formulas of the science of Galileo and Newton and so on were reduced to a single equation, everybody thought the goal was in sight, final truth. We're reaching the final truth about reality. Now, that dream, the dream of a final truth, the dream of, finally knowing everything about the world with perfect accuracy, is only possible when you think in terms of reified generalities. When you think in terms of science. The moment you begin thinking with the ideas that I've been trying to give you in the last 2 days, that is with all